So today's lesson is 9.1. It's all about intersecting lines. And we're going to look at 4 cases. Now, 2 of the cases we're probably familiar with in grade 9, right? If you're looking at 2 dimensions, you'll either have lines being parallel, or if they're not parallel, they'll intersect. But here we have a couple cases, a couple more cases we're going to go over. So the first one is yes. So 2 lines intersect. Now the second case is coincident lines. So 2 lines which are identical. So technically, in that case, there's an infinite number of intersection points. And we have 2 lines that are parallel, which means they don't intersect. But in 3D, we can have lines that are not parallel that still don't intersect. And they're over here. They're called skew lines. So there's the other option. All right, so let's look at the cases and what this looks like. So we'll go down and look at this later. Let's look at the first problem. So here we have an example of 2 lines. Line 1 is given by this vector equation, and line 2 by this vector equation. And we want to determine if they intersect, and if they do, where they intersect. So first, notice that if these lines are parallel, they won't intersect. So we can check that right away and look at their direction vectors. So for line 1, the direction vector is -1, 1, and 4, right there. And for line 2, the direction vector is -6, -1, and 6. So if these lines are parallel, then they should be equal to a scalar multiple of each other. But you can see that's not going to be the case. Right? So they don't equal, therefore not parallel. So we know they're not parallel. They still could be skewed though. We don't know yet. But they're certainly not parallel. And since they're not parallel, they're also not coincident either. Right? So we're left with 2 options. 1, they intersect at one point, or 2, they're skew lines and they don't intersect. So what I'm going to do is I'm going to take each line and write out their parametric equations. So for line 1, we have x equals -3 minus s. We have y equals 1 plus s. And we have z equals 4 plus 4s. We can do the same for line 2. Just write their parametric equations. So x equals 1 plus, minus 6t. So 1 minus 6t. And then y would be 4 minus t. And z would be 6 plus 6t. All right. Now what we can do is we can start by looking at our x and y coordinates. And if we set those x coordinates equal to each other, we can solve for a value of t and s for where those x and y coordinates would be equal. So let's start with that. So I'm going to set the 2 x coordinates equal. So here we have -3 minus s. So -3 minus s equals this one, 1 minus 6t. And I can rearrange that a bit. So I can write it as s minus 6t equals -4, just by rearranging our terms a bit. And collecting like terms, because we have a -3 and a 1 here. And we can do the same thing with our y's. So we'll have 1 plus s. I'll use a different color. So 1 plus s would equal 4 minus t. Okay, and then just clean it up a bit. So we'll have s plus t equals 3. So here you have 2 equations with 2 unknowns I'll call this one equation 1. I'll call that one equation 2. So I have to solve this system of equations. Certainly one way to do it, we see we have an s term here and an s term here, both with a coefficient of 1. So we can just take equation 1 and subtract equation 2. So s minus s is just 0. And then we'll have negative 6t subtract t, which gives us negative 7t, equals negative 4 minus 3, gives us negative 7. All right, so you get t equal to 1. All right, so now that we know that t equals 1, I mean, you guys have done this all before. You can substitute t equals 1 into equation 2. And we'll have s plus 1 equals 3. So s just equals, well, 3 minus 1 is 2. All right, so we have a value for s and t. So we know that those values of s and t, since we used our x equations and our y equations, we know that if we plug in t equals 1 into our equation for x, right, we would get a certain value. And if we plugged in s into this equation, we would get the same value. And we can actually check that, see what values they are. In this case, so substitute 2 into here for x, and you would get x equals minus 3 minus s, which is 2, and you get negative 5. And you can confirm that with here, right? It should work because we used x and y to actually solve for t and s, so it should work because we started by equating x's together. And you can see, well, 1 minus 6 times t, which is 1. Yeah, that works. Okay, so x equals 1 minus 6 times 1. That also equals minus 5. So that's a good check on our work. And we can check our work for our y's as well. And so here we have 1 plus s, where s is 2. So 1 plus 2 equals 3. And do a check here as well. So y equals 4 minus t, where t is 1. There you go. It works. Now the interesting thing is when we check for z. So z, we never used z to actually solve for s and t. So this is where we determine whether or not there actually is an intersection or if these lines are skewed. So we have our two, sort of our two lines, right? And we found the points where their x and y coordinates would be the same. So the question is, are they like this or are they like this? Are the z coordinates the same or are they not? So let's look at that. So if we look at z for line 1, it is 4 plus 4s. So 4 plus 4, and s is 2. All right, well, 4 plus 8, that gives us 12. And what about for line 2? This is line 1. This is line 2. So for line 2, we have 6 plus 6t, and t is 1. So we get 12. So our answer then is, do they intersect? Yes. They intersect. And where do they intersect? They intersect at these coordinates, minus 5, 3, and 12. So in the next example, this is already put into parametric equations for us. Great, we don't have to do that. And you can see still that if you look at your direction vector, which is here, all of your s's, so 1, 4, and 5, and over here, negative 1, 2, and negative 5. So you definitely can't write one as a scalar multiple of the other. So once again, we know they're not coincident and they're not parallel. So we're left with the same two choices. Are they intersecting at a point, or are they skewed and they don't intersect at all? Now in the previous one, I set x equal to x and y equal to y. you don't always have to do x and y. So what I'll do with this one is I'll do y and z. Right? So I can set y equal to y, and that'll give us the equation 3 plus 4s equals 17 plus 2t. Okay? And I can clean that up a bit. I can write it as 4s minus 2t equals 14. I can clean it up a little more by dividing every term by 2. And just write 2s minus t equals 7. So that's by equating y. So literally I just did y equals y from line 1 and line 2. And I'm just going to go over to the side a bit here. And I'll do the same thing with z. So I'll do like z equals z. Right, for line 1 and line 2. So when I do that, you get line 1, 6 plus 5s equals line 2, 30 minus 5t. And, okay, we can clean that up a little bit. We can write it as 5s plus 5t equals 30 minus 6 is 24. So now I have the two equations. Call this equation 1, this equation 2. And I have to solve two equations for two unknowns. And the equations I used were y and z. So whatever values I get, as long as I do it correctly, those should correctly tell me the same coordinates for y and z for line 1 and line 2. And then we'll check with x to see if those lines are skewed or actually intersect. So in this case, what we can do is, here there's a minus t term and a 5t. So I can take equation 1 and multiply it by 5. If I do that, we'll get 10s minus 5t equals 35. And then I can sort of just subtract those two equations. Subtract. Get, add. So 5 plus 10 is 15. S plus 5 and then plus negative 5 is 0t. And that's going to equal 59. So now I can just solve for s. This is not as nice as the last one, but s is 59 over 15. And I can take that and I can substitute it back into equation 1, which is 2s, which is 59 over 15, minus t equals 7. And you guys are good at rearranging equations. You can show that if you rearrange that, you'll get t equal to 13 over 15. And if you substituted those back in, you can get x and y coordinates, but y and z coordinates. We did y and z. But before we check y and z coordinates, let's just check x. Let's see if x would be the same, or if they're skewed. So in our first equation for line 1, we have x equal to minus 1 plus s. So that's negative 1 plus this wonderful fraction here, 59 over 15. Okay. So that's going to give us 44 over 15. So that's the value of x in line 1. Now if we did it for line 2, our equation for line 2 is over here. Oh, for x, 4 minus t. So x equals 4 minus t. All right, so that's 4 minus t is 13 over 15. And that actually equals 47 over 15. They're not the same. You can double check to make sure you solved s and t correctly by substituting it in for your y coordinates and z coordinates, and you should get the same value. But our x coordinate is not the same. Therefore, these lines are skewed. There's no intersection. Okay, lines are skewed. Okay, no intersection. So what you can see that we did in the first two examples, the main thing was solving two equations for two unknowns. Later, you're going to see that we're going to have three equations for three unknowns to do as well. And it can get a little tedious. So I am going to teach you a more efficient way of doing that. So we can go back to here. So let's say we have these three equations with three unknowns, x, y, and z. So we have equation 1, equation 2, and equation 3. What I can do is, the way I manipulate these equations, I'm really only dealing with all the coefficients. So what I'm going to do is I'm going to do these brackets, and I'm just going to write the coefficients. So the coefficient of x here is 1, so I just write 1. The coefficient of y here is 2, so I just write 2. Coefficient of z is 2, so I just write 2. And then I do a vertical line to represent this equals. And then our constant at the end, 9. And I do the same thing with the next equation. So 1, 1, and 0, 1, 1, and 0, and then our constant 1. And lastly, equation 3, 2, 3, and negative 1. And so notice that this first column is all your x terms, your second column is all your y terms, and your third column is all your z terms. And then what we can do is we can perform the same type of manipulations with the coefficients that we would have done with the equations. And when we write them like this has a special term in math. It's called a matrix. Not the movie, but this is called a matrix. Okay? And the manipulations that we do with them are very similar to here. So notice that right here, I did equation 1 times 5, and then I added equation 2. We do the exact same things. So let me go back over here. So these are what you're allowed to do. You're allowed to multiply a row by a non-zero constant. Okay? Just like we did before, equation 1 times 5. If you wanted to, you could interchange any pairs of rows, right? It doesn't really matter what order we write the equations in. And lastly, we can add one row to another row to replace that second row, which again is what we did before. So let me show you what this looks like if we're working with this problem. Notice that here I have 1 and 1. So what I can do is I can take row 1, multiply by negative 1, and add row 2. And notice I write this manipulation right next to row 2, because that's what I'm going to replace row 2 with. So if we do that, here you have negative 1, because we're multiplying it by negative, plus 1, that gives us 0. Negative 2 plus 1 gives us negative 1. Negative 2 plus 0 gives us negative 2. And negative 9 plus 1 gives us negative 8. And I can keep doing these operations. Now the goal is to get these three numbers to be 0. So notice the next step, my first step was to make this one 0. And then make this one 0. And then make that one 0. So 3 steps. And then you have this. Once you have this, notice what your equations are. This first equation is x plus 2y plus 2z equals 9. So that's this. Then we don't have an x term. We just have minus y minus 2z equals minus 8, which is this. And then in our last row, we don't have an x or a y term. We just have minus 3z equals minus 9. So once we have our matrix set to this little left corner triangle of zeros, we get these equations. And those are so much nicer than these, because you can see look at equation 3. Minus 3z equals minus 9. You can look at that and just say, well, z then equals 3. Once you know z equals 3, go look at your second equation, and you have minus y minus 2 times 3 equals minus 8. And there you go. You can solve for y. Y equals 2. Now that you have y equals 2, we can go to our first one, and we have x plus 2 times y, which is 2, plus 2z, which is 2 times 3, equals 0. And solve for x. There you go. X equals minus 10. So, yeah, there was a mistake here. This 9 magically turned into a 0. So that should be a 9. So solving for x, you'll get -1, not -10. So it's a little bit more efficient way of doing it. And if you continue taking math in university, you're going to use these a lot, as opposed to typical substitution. And there's a lot more you can do with matrices, especially with vectors, which I won't go into, but at least you'll see and understand the notation. Now this specific thing we're doing with matrices is called elimination. And making it look like this little triangle here, that form of a matrix is called a row echelon form. You don't really need to know that. But let's look at our last example, because we're going to try and solve these 3 equations for those 3 unknowns using our matrix. So I think I'm running out of space, so let me just copy this and do it on another page. Here we go. So here's our 3 equations. So first step is we need to write them as a matrix. So I'm going to set up my matrix right here below it. So our square brackets and our equal sign. Then we write our coefficients. So 1, -1, 1, and 1. Next one, so 2, 1, -1, and 1. And lastly, 3, 1, 2, and 12. So there's our matrix. So first step, I'm just going to write the first row as is. 1, -1, 1, and 1. Now the second row, I want this 2 to become a 0. So you can think, how can I make it a 0? Well, if I multiply the first row by 2, then that first coefficient will be a 2, right? And then I can subtract a 2. Now usually we don't like to subtract. What we like to do is add. So what I'll do is multiply the first row by -1. So I'm going to write what I'm doing here. So, sorry, -2, not -1. So multiply the first row by -2, and then add the second row. So that's the operation. So 1 times -2 is -2. And then we add 2, we get 0. -1 times -2 is +2. Adding 1, we get 3. 1 times -2 is -2. Add -1, we get -3. And again, 1 times -2 is -2. Add 1, -1. And then what I can also do is if I look at the third row, if I take the first row and multiply by 3, or sorry, -3, and then add the third row, then I can get 0 here as well. And that's the next goal. Now, if you don't like doing 2 operations on the same matrix, that's fine. Just be careful that you're not repeating certain operations over top of each other. So I'm doing row, so I'm replacing row 2 with an operation I'm doing to row 1, and then I'm going to replace row 3 with an operation I'm doing to row 1. So minus 3 times row 1 plus row 3. Right? So then I'll replace row 3 with that operation. And you can go through that again, and you'll get 4, -1, and 9. Let me just go down a bit. Oh, no, can't go down. I'll go up here. So the next step is to make that a 0. Okay, so if I'm going to make that a 0, I want you to be careful with something. Here's what I want you to be careful with. Now you might look at it and say, oh, if you look at row 1, you could simply multiply row 1 by 4 and add them. Yes, you could do that, and you would get a 0 here. But here's the problem. If you multiply row 1 by 4, look what happens to your x term. You'll get 4 plus 0. So you lose your 0 there. So what we want to do is work with row 2 and 3 so that these zeros stay. So what I would have to do is, I can't avoid it, there's going to be a fraction here. Okay? If I multiply row 2 by -4/3, then add row 3, then it will work. So -4/3 times row 2 plus row 3. Okay, and that's going to replace the third row. The second row is not going to change. It's still going to be 0, 3, -3, and -1. But doing this, I keep my first 0 and my second coefficient becomes 0. Then my third coefficient becomes 3. That actually works out quite nicely. And then you can't avoid this, but you get a fraction, 31/3. But that's it. Now if you look at it, you have your last row is 3z equals 31/3. So z is 31/9. Then you can look at your second row, which says 3y minus 3z, and z is 31/9, and that's going to equal -1. You can solve for y, which will be 28/9. And then your first row, which is x minus y, which is 28/9, plus z, which is 31/9, equals 1. And you can solve that for x, which is 2/3. All right, so messy solutions, because you got those fractions, but a very elegant, concise, efficient way of solving 3 equations for 3 unknowns.